Hello and welcome to our webinar, Tips to Support Your Teaching of Cambridge IGCSE International Mathematics with Nick Asker. I'm Eliza Sinatra from Cambridge University Press, and I'll be hosting this webinar for our speaker, Nick Asker. Thank you for joining us today. So Nick is an independent mathematics advisor. He started teaching mathematics in 1982 and has taught in a variety of settings, including secondary schools and all-age special schools. Nick regularly leads work groups for the National Centre for the Excellence in Teaching of Mathematics, and he is a tutor of their PD LEAD program. Nick has also led teacher education programs in Africa and the Middle East. I'm going to give attendees a little time to join the webinar before we start. And if you'd like to chat to one another and let us know which country you're joining us from, please feel free to use the chat box. It would be great to hear from you. I can see some answers coming through. We've got attendees from Vietnam and Nigeria. Welcome. And while you're waiting, I'm going to launch a poll to find out about your main challenges in the classroom. It would be very interesting to see what answers we get. And if we haven't included your main challenge, you can add this to our chat and see if your fellow attendees have similar challenges. So let me launch that poll. Okay, I think you can see our poll now. And I can see we've got some attendees from India. Welcome. Saudi Arabia, Malaysia. It's very international. Bangkok, Hong Kong. And I can see some poll answers are coming through as well. So far, time management is leading as the most common challenge with 36%, 33%, oh, changed very quickly, 35%, teaching with technology, 33% helping students work without a calculator. And I can see that 63% of you have already participated. So let's see if we can bring that number a little bit up and wait for other attendees to participate as well. I can see that 20% of you find supporting English as a second language learners the most common challenge as well. And time management is at 43% now. Okay, let's give it another minute. And I can see that the number of attendees is growing as well. So let's wait a bit more. And while we're waiting, let me explain how we're going to run the webinar. We're recording the webinar today to share with you afterwards. So don't worry if you have any internet problems, just rejoin us when you can. And if you're having trouble with your speakers, we suggest using headphones or checking that your speaker isn't muted. Your microphones will remain muted throughout the webinar. And if you have any technical issues or questions about our science products or maths products, please can you put those in a chat box, and my lovely colleagues Tamsin Hart and Arifa Khan will be on hand to help you. You can also put any questions for Nick into our Q&A box, and we will answer those questions at the end of the webinar. And 7 days after the webinar, we'll send you an email thanking you for attendance with a link to the webinar recording and information on where to find the webinar slides. Unfortunately, we can't provide certificates. However, you can use this email as proof of your attendance. So let's go back to our poll. I can see that 82% of you have already participated, which is fantastic. Time management is leading with 50%. Teaching with technology, 25%. And equally helping students work without a calculator, 25% as well. Oh, and helping students to gain 21st century skills, 25% as well. Well, let me give you one more second and I'll end this poll and share results with you. Okay. So our final results are time management, 52%, teaching with technology, 24%, preparing students, only 10%, helping students work with a calculator, only 3%, helping students work without a calculator, 24%, supporting a differentiated classroom, 31%, helping students to gain 21st century skills, 24%, supporting English as a second language learners, 14%, and 14% for student personal well-being. Thank you very much for participating. I'll stop sharing the poll results. And I think that's the end of our introduction. Just before handing over to Nick, I'm going to remind you that this webinar is being recorded. So if anything happens, oh, hi, Nick.
Sorry, I forgot to mute myself.
No, it's all right. Shall we start then?
Okay, great. I'm assuming, can you just check everyone can see my screen, Lisa? Is that okay?
Yes, I think we can all see your screen.
Brilliant. Okay, excellent. I'll start then. Well, hello and welcome to you all. Good morning here in the UK. It's a lovely sunny morning, only 10 degrees, but we're working on that. The summer is coming, but it's probably good afternoon or good evening wherever you are. I'd like to say it's lovely to see you all, but of course this is a Zoom meeting, so I can only see very small images of a very small proportion of you. But if I could see you all, I'm sure it would be lovely to see you. So what I'll be doing in this session is talking about teaching mathematics and how the Cambridge materials and resources can help you do this well so that your students can achieve the best that they can. Now, I take the opportunity to talk about teaching mathematics at every opportunity that I can, and it's been the source of much fascination to me throughout my teaching career, much to the disgust of my own children when they were younger, who got heartily sick of having a dad who was a maths teacher. But a lot of what I'm going to say today references research into mathematics teaching, which informs the content in the course book and the teaching materials that I'll be talking about. The title is Tips to Support Your Teaching, so that's exactly what you're going to get. I'm sure many of you will be familiar with previous versions of the Cambridge IGCSE International Mathematics syllabus. Now, I'm not the syllabus expert, and there is support online for syllabus content, but just a few quick headlines to go through here. Additions into the core are relationships between sequences, the term-to-term rule, and recognizing linear and quadratic functions. In both core and extended, lines in the form x equals k are new. There are some changes to lines of best fit and an expectation of making calculations with money. In the extended syllabus, symmetry and functions and solving trig equations are new. There are some items removed from the core, but they're still in the extended, such as asymptotes, transforming graphs, and cumulative frequency. If you need any more information about the syllabus, it's already been typed in the chat, actually, the link that you can follow to do that. So if that's what you need, that's the place to find it. Now, I do like to start with an obvious statement. So here is one. The course book covers the content of the Cambridge IGCSE International Mathematics 0607 syllabus. That's quite reassuring, I think, and not completely unexpected. The course book explains the syllabus, if you like. It adds the details and the substance to the learning objectives, which are the thing which are ultimately assessed in the examination. It's really important, actually, to think about it being the thing that interprets the syllabus and turns it into mathematics that the children can, or the learners can do, and that's its role. So most of what I'm going to talk about this morning relates to the features of the course book. There's a nice little picture of it here, but I'll also talk about some of the other teaching resources, which we call TR for short, which are also available for you. Then in the over 40 years that I've been teaching, I've seen some massive changes in the way in which we teach mathematics, not least because the amount of research carried out into things like cognitive science and actually how children learn has increased exponentially. And as a mathematician, I do like a bit of exponential change. This means that the elements that go into making an effective textbook to support the teaching of mathematics have also changed over the years. And what I'm going to do is show you some examples from the Cambridge resources that will help you teach this syllabus in the most effective way. The image that's on the screen now came from some professional development that I was running a few weeks ago. It does feature evidence of my appalling handwriting, for which I apologize. If you can't make sense of that, this is I asked this group of teachers for their suggestions for what they would hope to be able to provide in their own maths lessons. Now, this group of teachers are extremely inexperienced. They are only in their first year of teaching. So it's quite encouraging to see that they had all of these things that they were trying to get into their maths lessons. And what's interesting is to reflect on what research says about how useful and important these things are. But they do talk about engagement, by which we mean getting kids interested in it. They liked the idea that there was a challenge in the lesson and that there was some proper wow going on, that the kids were kind of having those moments of, oh, so that's what it means, or, oh, that's how I do it. They were very keen on exposing misconceptions, about which more later. They talked about questioning and thinking and having structure and routines in their lessons. They talked about clarity, being clear. They talked about the need to model things. They talked about putting maths into a real world context. They talked about the mathematicians or the students themselves becoming confident, independent mathematicians. And the one at the bottom is one that I stuck in myself because it's something that stays with me from some research I did a long time ago about needing to have the opportunity to generalize in a maths lesson. So whenever we learn something in a maths lesson, we need to sit and think about what does it mean in context of other pieces of mathematics, and can we do anything else with it? So as I say, I was really encouraged by that. And because I was about to prepare this webinar, I thought to myself, actually, this is quite a good starting point. These are things which are worth looking at. These are things which are worth considering in our teaching. Most of you, I'm sure, will be familiar with the work of John Hattie on visible learning. John Hattie has been a professor of mathematics in several universities in New Zealand, in Australia, and in South Africa. And his research, or rather actually it's meta research. It's one of those things that groups together a whole load of research. But his research shows that students learn better when they know the learning intentions in a lesson and what that actually looks like in practice. So in other words, the students need to know what they're trying to achieve and how they'll be able to recognize it when they do so. So for this reason, every chapter in the course book has learning intentions. And here's an example there. These give a big picture view of what they will be learning to do within the topic. And it's pretty standard fare for a textbook. You'd expect to see that. This particular example comes from chapter 6, which is all about indices and powers and surds. But there's also a summary at the end of each chapter, which is an opportunity to reflect back on their learning. Now, in the example that I'm showing on screen now, the ones in white, or on the white background rather, they are the core objectives. And the ones which are in the blue, they are the extension objectives. Now, from a teaching point of view, it's important to remember that these are in the course book there for a reason. They are there to prompt you, the teachers, to make the learning intention obvious to the students. My own experience is that if I don't point them out, then the students won't see them, or they certainly won't look at them. Similarly, the summary is a good place to allow some time for this at the end of a unit. Now, the research says that having them there isn't enough. We have to make them explicit. We have to point them out. We have to say to children, look at this, can you do these? Or to give them some time to do these self-reflection activities. I could talk now a little bit about metacognition. This may or may not be a term that you're familiar with, but it's an idea that's not new, but has only been widely applied to teaching in fairly recent times. There is a strong body of research demonstrating the importance of metacognition and actually self-regulation, which is a separate thing I'm not going to talk about now, but the importance of metacognition to effective learning. Metacognition is about the ways that learners monitor and purposely direct their learning. It's sometimes described as thinking about your thinking. In mathematics, one simple way to get started with it as a teaching strategy is to encourage students to look back over their work and the questions that have been completed, and to reflect and to think about the approaches and the strategies used. So you're trying to get them to look at things from a level higher than just, was this the right answer or was this right? I have reproduced one example here to illustrate how simple it can be to get started with this approach. Essentially, it's asking students to just look back at these questions and think about how they did them. Now, these reflection opportunities appear throughout the course book. And until students are practiced in this, though, teachers may find it helpful to find time for this as a class or a small group activity. If you're interested in finding out more, the EEF guidance report, which I've referenced on the slide, is freely available online, and I'll share the full title about it later on. It's an interesting document. But it's an interesting quote that evidence suggests that the use of metacognitive strategies, which get pupils to think about their own learning, can be worth the equivalent of an additional 7 months progress when used well. I think we'd all take an extra 7 months progress in our students if we thought it was available. One of the most influential pieces of research into education, in particular the use of assessment, was published by Black and William from University College London in 1998. Now, although it's 25 years old, it remains a relevant piece of research into how assessment, in particular what we call formative assessment, can be used in the classroom to improve student outcomes. This piece of work is relatively well known, but less well known is the 2006 follow-up publication by William and Jeremy Hodgen called Mathematics Inside the Black Box. For teachers looking to reflect on their practice, it is also readily available online, and it looks like that. One of the ideas that both of these publications have in common is that teaching needs to start from where the learner is. There are plenty of other pieces of research around at the moment which will say exactly the same. Teaching must build on prior learning. And one of the ways that you can do this as a teacher is by checking understanding of the prior knowledge. In other words, what do they know already? What position are the students starting from? So that's the intention behind the getting started section at the start of each chapter. This can be used as an opportunity to check that students have the appropriate skills for the work ahead, and might also inform the teacher of skills that need revisiting or revising. Similarly, in the teacher resource, there is a section called Background Knowledge, which has the same function. So this is the start of the chapter on SIRS, and you can see what they're being asked to do there. We're reminding them about index notation, we're reminding them about prime factors, and we're asking them to evaluate some calculations involving negative numbers and fractions. Okay, I'm going to give you a chance to put a quick answer to a question in a chat. I believe the youngsters call this a chat blast. It shouldn't take too long, and I just want to just ask you a particular question. So I'm going to click on the screen. A question is going to appear. Can you please read it and then indicate in the chat box whether you agree with statement A or statement B? So I'm going to give you 30 seconds to do that now. Okay, thanks. That's very interesting. It's probably helpful to define what we actually mean by a misconception at this point, isn't it, really? Because sometimes there's a little bit of confusion, or maybe even a misconception, about what a misconception is. Technically, it's an understanding that leads to a systematic pattern of errors. So it's not a simple mistake. It's not the kind of mistake I used to make as a child would be something really daft, like saying 3 times 2 equals 5, and that would be just a careless mistake. It wasn't me misunderstanding multiplication. It was just me scribbling things down and not thinking clearly properly enough. So often misconceptions are formed when knowledge is applied outside the context in which it is useful. For example, when learners first learn simple subtraction, the way in which it's presented means they always subtract the smaller number from the larger number. This can be internalized in their heads as a kind of part of the rule for subtraction, so that later on, when they're faced with, say, 3 subtract 7, they insist that the answer is 4 because they've taken the smaller number away from the larger one. That is an example of a misconception. Now, just looking at what people have put in into the chat there, it's interesting. There's a mixture of A's and B's, but I'd say it's predominantly B's. Now, I asked this exact same question in 2014 at a large conference in London, and had an almost 50-50 split, which is interesting. And so I think over the period of time, people's idea and understanding of misconceptions has probably changed. I think the correct answer here is B. I think it's much healthier to encourage learners to make mistakes and to learn from them and to confront misconceptions. And actually, I've already referenced the Education Endowment Fund, the EEF, when talking earlier about metacognition. This is from the same guidance report. It's actually called Improving Mathematics in Key Stage 2 and 3 EEF guidance report. For background, the EEF is an independent charity in the UK which supports schools to improve teaching and learning through better use of evidence. So everything they publish is evidence-based, and they put together a document about 4 years ago now called Improving Mathematics in Key Stages 2 and 3 Guidance Report, and it is full of evidence-based suggestions on how we can teach students more effectively. Now, the one I've, so although that's about talking about key stages 2 and 3, I think the principles hold true for students of all ages. And it's very clear that the evidence says that misconceptions should be uncovered and addressed and not swerved and avoided. Actually, I suppose it's a matter of style as a teacher as to how you do that and when you do that, but certainly you need to be aware of them and we need to do something about them. In the teacher's resource, which is a separate publication which will be available at the same time as the course book, there are a couple of examples in each chapter of common misconceptions that relate to the ideas covered, and there's one of the examples there about misconception that might occur with Pythagoras' theorem. Now, one of the tricky things about misconceptions is that you can't predict them all. So there's only a couple of examples in each chapter because they're by no means exhaustive, but they are a starting point. You as teachers will be aware of some unexpected misconceptions that you've come across, but where they appear, they always need addressing either immediately or at the next available suitable point. This quote is from Galileo. There's no doubt that mathematics is a language, and with all languages comes the need to know the vocabulary, the grammar, and the syntax, or in other words, the words, what they do, and in what order they should appear. Mathematics is in some ways a universal language, and we want our students to be fluent in it. So for this reason, we have to be carefully precise when introducing new vocabulary, and in the context of the International GCSE, are aware that learning mathematics through English as a second language is an additional complication. So the authors have been careful to try and write it in very clear, plain English, for exactly that reason. In the teacher's resource, there's a short paragraph in each chapter highlighting some potential language support that might be needed. And throughout the course book, keywords are highlighted as you'd expect. Students will achieve better if they can understand and use this technical vocabulary. Interesting research in the UK by an organisation called Voice 21 reports that speaking the words is as important as writing them. So as teachers, we should be very precise in both our own use of vocabulary and expecting similar precision from our students, but also inviting them and encouraging them to say the words out loud and to use them. Unsurprisingly, as I say, we've got keywords identified in each chapter. These are from the indices, standard form and surds chapter. And you can see there's some quite technical words in there, aren't there? Conjugate surds, rationalize the denominator. They're not things that you would say in normal spoken English. They are very specific to mathematics. And so we have to use them in mathematics, and we have to make sure that our learners use them too. I have deliberately chosen an image here to represent a schema. Because I want to delve briefly into a theory of learning called constructivism. Now, it's going to be brief, so don't worry. Constructivism's central idea is that human learning is constructed and that learners build new knowledge upon the foundation of previous learning. Now, we've already discussed how the getting started sections can help build upon prior knowledge, but it can be helpful to also consider the idea of a schema. A schema describes a pattern of thought or behavior that organizes categories of information and the relationship amongst them. Constructivists would say that rather than passively receiving information, learners reflect on their experiences, create mental representations, and incorporate new knowledge into their schemas. Now, the example I gave before about the misconception in subtraction, there was the learner had a schema. The learner had the schema that said if you take 7 away from 3, you're going to get 4. The problem is that's an error, but there was still a schema there. And all we do as we learn as mathematicians and in other fields is that we adjust our schemas as we go along. So addressing that child's misconception would hopefully adjust their schema so that they realize that that wasn't always true. Now, I find it really helpful to think of mathematics as a series of interconnected ideas that describe the world rather than a set of ordered processes that take me step by step to a perfect solution. Part of developing the interconnected nature of my schema is making the connections between pieces of mathematics when they become apparent. Now, despite my very advanced age and enormous amounts of experience, these still happen all the time. And there's an example on the screen there. A few years ago, I was doing some training for teaching assistants who aren't qualified teachers. And we were talking about mental calculation strategies. And the example that I had on the board was 84 divided by 14. And I said, I don't think I'd do that in my head because I'm not very good at my 14 times table mentally. And one of the trainees said, well, I would. And she pointed out to me that 84 divided by 14 can be written as an improper fraction, which if I cancel it down becomes 42 over 7. And I can do that in my head, it's 6. Now, I knew all those various pieces of information. What I've never done is put them together to think of division as a fractional process. And so now whenever I come across anything that I want to divide mentally, I now in my head turn it into a top-heavy fraction or an improper fraction and see if there's any sense of something I can do to cancel it down to make it a more straightforward calculation. So my schema has changed and my schema has advanced. And this is one of the purposes of the tips that appear frequently within the course book. We're encouraging students to make connections and to build their schema so that they understand and retain knowledge. Again, you have to be a bit careful here, though, because mathematics is so interconnected that it would be impossible to make all of the connections. But we should do as many as we can without overloading the students. So the obvious ones, they're there within the course book, and we should make the most of them. Similarly, that's the purpose of the mathematics in context box, which you'll see in various chapters. These also endeavour to build the schema by making connections to other non-mathematical contexts. We want students to be able to understand and use standard form when it appears in science, as in the example here. Once again, I'm quoting Inside the Black Box by Black and William here as a reason why we've added opportunities to discuss within the course book and the teaching resources. Note, though Black and William talk about increasing knowledge and improving understanding, we don't have the time here to delve into the many different types of knowledge that are identified. Safe to think of it in tandem with understanding, or use a definition that gets used in the UK at the moment a lot. Knowledge is what's left behind after learning has taken place. So if we use the example above, which I've just clicked on, the discussion here would be intended to ensure that students have a deeper understanding of why the exterior angle of a triangle is equal to the two opposite interior angles. The quote at the top of this slide is from the Introduction to the IGCSE Maths syllabus. Note the referencing to reasoning. Now, you may or may not be aware of the respective maths organisation called EdRich, which is based at the University of Cambridge, who describe reasoning as it being fundamental to knowing and doing mathematics. It enables learners to make use of their mathematical skills and can be thought of as the glue which helps mathematics make sense. I really like the idea of that reasoning is the glue which helps mathematics make sense. Because if we don't think of it like that, if we just present a whole load of things to learn or things to do, we're not actually encouraging children to reason and to think. So that's why it's in the mathematics syllabus, because it's important. But teaching students to reason is not easy, and it rarely happens by accident. One of the approaches we can take is to ensure that they have plenty of opportunities to reason through their maths lessons. And one of the ways in which you can do this is to have investigations. So here's an example of an investigation. We're trying to get students to do some thinking for themselves and to develop their reasoning by having these investigations in the course book. This particular one is quite structured, as anything that's too open-ended tends not necessarily to have the intended outcomes. And again, there's lots of research into the ineffectiveness of what people used to call discovery learning. So sometimes the investigations don't feel that they're that investigative, more that they are opportunities for independent work. Activities in the teacher's resource have a similar role. For example, this activity allows teachers to talk about proving Pythagoras' theorem, and proof being a higher degree of reasoning than just understanding it. Note that in this activity, the teacher is tasked to model and explain their thinking. This is one of the ways in which reasoning can be taught. So it's that last sentence there. As you work through the activity, model and explain clearly your thinking at each stage of the demonstration. Encourage students to complete the steps one at a time. So I'm always interested in proofs of Pythagoras. So this is where this one ends up. This is the diagram that's used in the previous activity. Obviously, you're maths teachers, so you now want to know what the answer is to that or how that works. So I'll give you 30 seconds or so just to do to work that out. If anyone knows the solution and wants to type it into the chat, that would be helpful. But I won't be marking your homework, so that's up to you. Have to say it's a bit of a naughty question really, because it's not that easy to type mathematical things into the chat anyway, but and also we haven't got a huge amount of time here, so let me just show you what I mean by that. So in this diagram we have 4 right angled triangles, which are A, B, C, and we've got one square in the middle, which is C, and we've got A plus B around the outside as the dimensions of the square. So if I'm trying to prove that A squared plus B squared equals C squared, the area of the triangles plus the area of the small square is going to be the area of the whole large square, isn't it? So that plus that plus that plus that plus that must make the area of the whole square. So the area of each triangle is half AB, half the base times the height, and there are 4 of them, so that's 4 times half AB, plus c squared, which is the square in the middle, must be the same as a plus b all squared, because that's the area of the entire square. So if we just do the maths, we get 2ab plus c squared equals a squared plus 2ab plus b squared. Subtract 2ab from both sides, and we get a squared plus b squared equals c squared. Now, that activity is in the teaching resources, and it's talked through. The script is there for teachers to talk that through with students so they can understand the power of a proof, because actually there are no dimensions to any of those sides there, so it must always work. Okay, I'm going to say something about worked examples. It won't surprise you to know that the course book has extensive worked examples to support new concepts and ideas as they're presented. This example is from the same chapter 6, the ones about surds, indices, and standard form, and gives a clear explanation of 2 different strategies. These play 2 roles. They're helpful for teachers to add some extra support if needed when students struggle to understand, and they're also for students to either self-study or look back on to ensure that they understand the concepts that they're being taught. This is an example from chapter 3, which is using numbers. The important point about worked examples is that they should be clear. Incidentally, my experience of trying to teach children questions like this with to do with time problems is that a double timeline approach can be very helpful. I'll show you what I mean by that. So this is a double timeline. The 2 lines run parallel, but the bottom line is shifted 1 hour to the left, as Bahrain is 1 hour ahead of Cairo. So as you can see, the flight takes off, takes 3 hours, 20 minutes. When it lands at 1 p.m. in Cairo, it's 2 p.m. in Bahrain, which is really quite helpful. Okay, I'd like to say a little bit here about variation, and I'm going to start by quoting a guy called Mike Askew. Mike's been Professor of Mathematics Education in the UK, Australia and South Africa, and is highly respected. And if you've ever had the chance to go and listen to him talk, he's a very entertaining and interesting person to listen to. The central idea of teaching with variation is to highlight the essential features of a concept or idea through varying the non-essential features. In a way, it's similar to the idea of progression, and in practice exercises within the course book, you'll find this principle being used. So in this example of simplifying some surds, the first question, the first 2 questions are both in terms of root 3, and the second pair is in terms of root 2. So pairing the questions in this way may help direct students' attention to the connection. For example, both 18 and 27 are multiples of 9, hence they simplify to a coefficient of root 3. The final 3 questions down the bottom here are more challenging and extend students' thinking. But exercises have been written with this variation of thinking in mind, that you're trying to build on the prior learning, and also that you're trying to isolate the factors which are making something as it is. As we've already seen, the course book is full of tips that help make mathematical connections, but they also are used to give some guidance on strategies and methods. There are a considerable range of them. These 3 have been taken from chapter 6 again, indices, surds and standard form. It's good practice as a teacher to point them out and to make them explicit to students. There is good advice here that we don't want to go to waste. Although the best way to ensure exam success is to teach the syllabus well, that's obvious, I guess, there is a lot of benefit from students in making them aware of how the curriculum is examined, and all teachers use past paper questions as a way of assessing the progress of their students and how well they have understood and remembered content. In the UK at the moment, we're just running up to the GCSE maths, so maths teachers all over the land are busy using past paper questions to try and prepare their students for it. Each chapter in the course book has a short collection of questions taken from the recent examination series for this exact reason. The one shown above is at the end of the surds chapter. Now, obviously, I know you're all maths teachers, so you're going to want to think about what the answer is to that. We haven't got huge amounts of time, so I'll tell you it's root 5 minus 1 over 2. Okay, the quote I've used here is from the aims of the syllabus. And the list below is what candidates should be able to do with a graphical display calculator. As you can see, it's quite extensive. So in the course book, some of the examples are related specifically to graphic design, graphic display calculators. But that list over here is all of the things they should be able to do with one. So we've used some of our worked examples have been written in the form that will show you exactly what keys to press and how to work your way through. So this example relates to using standard form on a Casio calculator. Now, it often bothers me that that students are a bit ahead of me in terms of their use of technology. So my advice would always be to make sure that you are really familiar with the graphic display calculator that your school uses by just practicing with it. You're probably all familiar now with the theory of retrieval practice. We haven't got the time to go into that here, but the long and short of it is that if you become proficient in a skill, like using a graphic display calculator, you need to use it to maintain the skill, and that applies equally to teachers as it does to students. Paper 6 of the examination is what's called an investigation and modelling paper. It's for extension students only. There is a specific chapter in the course book that tackles this area of the curriculum, as it can be difficult to teach, but this paper is also why there are investigations and modelling activities running through the chapters. Alongside the course book, there are teacher resources available which have been written to give teaching ideas and some extra pedagogical input to support teachers. So what you might find in a starter in the teacher's resources, you might find some fluency practice, you might find some different ways of teaching, you might find some short practical activities, some recall practice, some ways of checking prior knowledge. So they might have any or more of those things there. Here's a quick example. It's a discussion activity designed to expose and deal with misconceptions around percentage increases. And basically you've got students doing two similar things, and you're asked, or the children are asked to discuss whether they're both correct or whether they can be both correct. And it's designed to pull out misunderstandings and misconceptions around what you're finding a percentage increase of, which is a fairly common one. This one, asking students to stand up and demonstrate their understanding of rotation, is a way of assessing their prior knowledge. It might draw out the idea they're not sure which is clockwise, which is anti-clockwise, etc. And this one is in the form of a script for a teacher to model a mathematical process. This actually is the suggestion for introducing vectors. And the idea is that you introduce vectors by getting students to understand the need for a vector and how it can describe movement across a plane. Like the starters, the plenaries try to add a few suggested different dimensions to the text that's in the course book, often by giving extra opportunities for students to apply their work in a different context or to solve a problem. This example is a real-world problem of the growth rate of an infectious disease, and it's used as a context for exponential growth. This is quite topical, I guess, because we've all lived through this recently, and actually goes on to explain how the R growth rate is used, and the question that's asked there actually is quite interesting. Is if we started off with 10 people infected and we have a growth rate of 1, and the disease is spread in this way for 10 days, how many people will be infected after the 10 days? It's a huge number. Students will be not only surprised by the huge number, it's exponential growth after all, but then it also gives you the opportunity to discuss why that actually wouldn't happen in real life, not least because we'd have lockdowns, or people wouldn't mingle, or people would be too ill to go out and mix with the same number of people. There's also some main teaching activity ideas in the teaching resource, and in chapter 15, the teacher resource contains a different teaching approach, a different pedagogical approach to introducing the trigonometrical ratios, and uses something called the unit circle. This can be, now, if we were face to face, I'd be asking people if they had any understanding or knowledge of the unit circle, and I'd be able to gauge the nods or otherwise. But I'm just going to assume that you either have or haven't seen this before, and I'm going to show you what I mean. This type of approach to teaching the trig ratios can be particularly useful when using geometry software such as GeoGebra or Desmos or Autograph or any of the other ones that are available. So I'm just going to show you a GeoGebra page. So hopefully you can now see that. So what I've got here is what I would call a unit circle. And effectively, there's a right angle triangle, A, B, C. Can't quite see C, it's hiding under there. There we go. A, B, and C. Now, when we first talk about trigonometry, we quite often forget about the word ratio. And actually where trigonometry comes from is it's the relationship between the sides in a right angle triangle dependent upon the angle. So as I change the angle, and as this angle gets larger, we might ask the students, what is happening to the length of AC compared to the length of BC? Are they both getting bigger? Is one getting bigger and the other one getting smaller? Likewise, as I reduce the size of my angle, what's happening to the sides? And we could stop at certain interesting points. Oops, if I can get my mouse to do so, like that, for example. There's something interesting going on there, isn't there? The length BC is half of the length AB, which is our hypotenuse. I wonder if that's always true. Well, if I expand my circle so that the hypotenuse length increases, just check out what's happening to the distance AB or BA and the distance BC. That ratio, that relationship stays the same. So the distance BC is always half of the distance AB when the angle is 30 degrees. And what I'm bringing in there is similar triangles, but I'm also bringing in the idea of ratios. Now, because that hypotenuse is 1, actually, the length BC does actually represent the sine ratio. So it's quite an interesting way of teaching that. And it's an example of one of the things that we've done in the teacher resources to try and come up with slightly different ways of teaching things as kind of hints and suggestions for what you might do as teachers. Okay, it's almost time for me to stop talking, but there is also further support available on Cambridge Go, which is online support. You'll see in this diagram here all the various publications which are available. That's our course book down the bottom there, the International Mathematics one. All of that stuff is available, and the folk from Cambridge will be able to give you more information about that. So that was a quick tour through the Cambridge resources and how they can support you to teach the IGCSE. Really, I would encourage you to remember that all of the features that are in the materials are there for a reason. They're not just there to make it look nice, and that using them will help your students succeed. So I'm going to stop sharing my screen now and hand back to Elisa, who is going to take us from here.
Well, wow, that was an amazing presentation. Thank you so much. I'm not a mathematics teacher, but I definitely learned several teaching concepts and learning concepts today myself. So thank you again, Nick. Now we will ask all our attendees to submit their questions into a Q&A box. And while you're doing that, please let me remind you that 7 days after the webinar, we'll send you an amazing, an email thanking you for attendance with a link to the recording of the webinar and the webinar slides. And you can use this mail as proof of your attendance. So let's have a look at the questions. Okay, you can see that some questions have been already answered by my colleagues, Tamsin and Arifa. Oh, meanwhile, I can say compliment in our main chat, saying that this is the best Cambridge training I've ever taken. Thank you very much. Oh, well, it goes to you, Nick.
I didn't know my mom was watching.
Okay, we'll just give attendees 1 more minute to think about possible questions. I can see someone is asking a question in the main chat as well. May I ask, is knowing distance time graph, e.g. travel graph, velocity time graph, is inside the textbook?
Off the top of my, as far as I can remember, yes, because it's in the, there's questions relating to that style of graph in the modeling chapter. I can have a quick check whilst anything else comes in. I'm pretty sure it's in there.
Yeah, but don't worry, we will be covering some of the questions we received today in our follow-up blog post later. So if you have any questions, please submit them, and those questions which we will not answer today, we'll pick up in our blog post. I can see more thank you words in our main chat. Okay, no questions at the moment, but let's give it just another second. So while we're waiting for questions, I'd like to remind you that to find out more about the resources discussed today, please speak to your sales representative or visit the links my colleague Tamzin has been providing in the chat. And once this webinar ends, there will be a short survey to complete. It will open automatically on your screens, so we will be grateful for any answers you provide. So let's see if there are any questions. Is international mathematics open to Nigerian students?
Well, yeah, as far as I'm aware, yeah. Why wouldn't it be? It's open to anyone in the world, as far as I know.
Absolutely, yes. I must say it's the first time everyone is so satisfied with the webinar. There are not so many questions.
Or stunned into silence, maybe.
Oh, I can see one question coming through. Do the links provided show the whole content of the book? I'll take that one. So this is just a sample. So you can see some sample pages of the book. But if you want to buy a book, please speak to your local representative. Okay, well, in this case, yeah, I'll just remind everyone that this recording will be shared with you within 7 days after the webinar, as well as the slides. When the webinar ends, there will be a short survey to complete. It will open automatically on your screens. We will be grateful for any answers you provide. And I don't see any more questions, so I think I will stop here. We thank everyone for attending today's webinar. There will be a blog post follow up, and yeah, please attend our further webinars as well. My colleague Tamzin has provided some useful links in the chat as well. We hope to see you there, and good luck with your teaching. And goodbye for now.
Absolutely. Thanks. Bye.